Well, I guess it's time to start then. Okay. So we got GANs today. All right. Who's heard of a GAN?
I have.
Oh shit! Someone
Aha.
has. Okay.
I
Cool.
have as well.
Oh, okay. 2 people have. It's not cool anymore, Nick. All right.
Fuck.
Let's start with let's start with some not machine learning stuff, just club stuff. All right. So I want to give away stuff, right? I want to give it away. I have stuff. I showed you the stuff last time, so you know it's real, and I want to give it away. All right. So here's what I'm thinking. Here's the stuff, right? We got a Raspberry Pi 4 kit. Comes with a bunch of stuff, like a little case. Comes with a heatsink and all that good stuff, right? And I got a Google Home, you know, one of the big ones. So that's good, I guess. And maybe more. It's a secret. Maybe there's not. Maybe there is, but maybe there's not. All right. So how do you get this stuff, right? If you want the stuff, how do you get it? Well, I'm gonna do a contest. I know I've talked about a contest in the past, and there was general unenthusiasm about it, I'll say. Probably my fault on that, but now we're going to have slightly more enthusiasm, hopefully. So I'm going to give you some data to classify. We'll do a classification problem since I don't want to give you a weird task, I guess. And then I'm going to score people's solutions on accuracy, speed, and creativity. And they're going to be worth the same. So you could have a model that gives me 100% accuracy on Safari 10, right? Or Safari million, and on ImageNet, 100% accuracy on ImageNet. But if someone's is faster and more creative, they'll kick your ass. So just saying, it's a balancing act here. You'll probably need some creativity to get 100% accuracy on that, but I don't expect any of you will do something like that. I'll release a notebook with some infrastructure code and some stuff in 2 weeks, right? Yeah, 2 weeks on the 30th. And then I'm going to give you 2 weeks to create the best model you can, or the best method you can if you really just want to skip out on neural networks. And then I will judge them all. So you'll basically just have to fill out your notebook and then send it in to me, and I will look at them. All right. So I'm also going to include a special sort of like side prize, I guess, which is if you win this, then I will promise to like advise you in your machine learning pursuits for the foreseeable future. I mean, that is maybe worthless, but is also maybe worth something. I don't know. I might be a teacher, and then that'll mean something.
You're really selling yourself.
I know, right? Yeah. I mean, who doesn't want that? All right. Yeah, but like I've sort of done this in the past. Like other people who have done the contest, when people have done very well on it, I do kind of take them on and advise them a little bit because I believe in them. I believe in all of you. Sorry, but I believe in them a little bit more. Yeah. So like I will be there to help you and like walk you through all the ML stuff, which I said foreseeable future, which was maybe a mistake. You guys are some of your freshmen. Anyway, so let's get back to the real stuff. We can just forget about that now. Now it's ML time. So this is convolution, right? I hope to God that all of you remember convolution, unless you didn't attend the lecture. Does anyone not remember convolution? Oh, I'm staring at the camera and waiting. There you go. I forgot to say. Okay, well that sounds good. I'm glad that everyone remembers it. Okay, so that's convolution. So we talked about it in we talked about very like basic things about convolution, and we didn't really talk about it very much. We talked about this a little bit, which these, as we found out, were filters that were being learned by our convolutional neural network. And then in doing layers of convolution, we saw that the features became more and more abstract, or the filters became more and more abstract. Actually, these are the filters. Became more and more abstract until they really had no visible meaning to us. And this is a very important concept to understand. And we can see how these features may be like very useful for classification. And in fact, some other thing that is very important for you to know, but I did not remember to include in the slides today, but I'll talk about right now, is that each of these features right here, as we have multiple layers of convolution, are influenced by a greater number of convolutions in the previous layer. So a feature right here may be influenced by like 9 filters over here, 9 features over here. And each of these may be influenced by like 16 of these. So as we like look at this, if we look at one of these, it could be influenced by a large chunk of the original image. And so these features actually have an ability to have more information in them. So that's an interesting thing to think about. We'll talk more about like these filters and stuff in a little bit though. All right, so let's start on more about convolution. So something I really just didn't talk about at all is, let's say we have some input of size 32. All right, 32 by 32, that's just an image that's the size of a Safari image, right, without RGB. So we have a convolution of, say, let's say 4 by 4, okay? So we sort of didn't talk about this at all. So stride is how far we move over each time we do a convolution, right? We'll move it over by, if stride is 1, we'll just edge it over a tiny bit. We'll like move it over by 1, move it over by 1, and keep doing our convolution like we do in this original image. This is stride 1. It's just moving over 1 at a time, moving down 1 at a time, okay? So if we have these shapes of our input and our convolution, and we have our stride, let's say that the stride is 1 in this case. I'm going to ask you all to try to solve this on your own, and then we'll go over the solution a little bit. But how big would the output of this convolution be? So we're overlaying this convolution, this 4x4 kernel, over this image. We start in the upper left-hand corner, and we move it over 1 at a time. And every time we do that, we get 1 output feature, right? So after we do that across the entire image, what would be the output of our convolution? What would be the size of it? I'm going to give you like 30 seconds to think about it. If
28 by 28.
28 by 28?
It's just a guess. Yeah.
That's a close guess. It is a very close guess. So
29 by 29.
That's a closer guess. That's the correct answer. Yeah. So we do get 29 by 29. All right. So how you can think of this is we're moving it over, like we're moving it over that many times. We're moving over stride times minus however many times we can like put this in here. So when we get here, when we're 4 away from the edge, we have to stop. We can't move it over anymore, otherwise we would be outside of the image, right? So we have to stop there. And it so happens that the number of times we can fit it in there is exactly this size minus that plus 1. So the plus 1 comes from the actual like tile laying that we can do. So keep that in mind. We'll get actual formulas for all this in a bit if you like are curious about how we could like actually have this out. But let's try changing something. Let's say stride 2. It becomes a harder problem instantly when you start thinking about it in stride 2. It's still pretty straightforward, but what would the actual size end up being? I'll give you, again, like 30 seconds to try to figure it out.
15 by 15.
Okay, well that was not as long as I wanted to give you, but that also happens to be the correct answer. Yeah, someone's seen convolutions before, whatever, or someone is just quick.
No, it's just like math.
Okay, yeah, nice. Okay, yeah. Yes, it is 15 by 15. So you can justify this to yourself. Essentially, we are halving the amount of times we can move over in general, but we still have to add 1. So I'll give you an actual formula for it. So what we actually have is that the output height, right? So the height of the output will be the input height minus the kernel height divided by the height stride. So something that I haven't really talked about at all, but we'll clarify quite a bit more, is that the kernel does not have to be a square. our stride can be different in different dimensions, and really in general we have multi-dimensional things and parameters like across all of this. Okay, so same with width, we basically get the exact same thing. I'd say take a second to write these down because it will be helpful for you, right? You write these down. Okay, cool. So, oh man, oh, it all comes out at once. Oh man. Okay, well, I'm gonna make you do it without actually showing it to you. What happens if we have stride of 5? Okay, I guess I did the things wrong on this slide, but stride of 5. Okay, someone tell me when they come to an answer. I'll show that there. And by 5, I mean 5 in both directions.
Is this
I think
infallible?
I have an answer.
I'd like to hear the one who said there is an answer first.
Okay.
Yeah. Was it Nick?
Oh, do you want me to answer?
Yeah.
I think it is 6.
That I could see why you would say that. Ryan actually got it correct, and let's do it out here. All right. So I did it all in one step because I messed up the animations, but there you go. So if we do it out, you see that we get 32 minus 4 divided by 5 ends up being 6.6, which you can't have. So what this would mean is that as we laid it over, at a certain point, we would have an overhang, right? And you just cannot have that. That doesn't make sense mathematically, and it doesn't work in practice. So in reality, this would cause an error. So we can't actually do this size. So our stride of 5 doesn't work there. So we need to keep track of like the size of both of these and the interactions between them to decide what strides are actually possible. All right? And don't worry, that's not the only thing we need to keep track of with these. All right. So let's introduce a way to deal with that, all right? So we have our image, right? It's 32 by 32. And let's say we want to do that 5 by 5 kernel with, or 4 by 4 kernel with stride 5. Let's say we want to do that. What we can do is introduce 0 padding. So around the outside of our input, so an extra 1 on every side, we will put all zeros. So we'll just put zeros around the entire outside of the image, and it will increase the dimension of the image, okay? So now we have a 34 by 34 image, and I want you to notice that like this is a padding 1, but it's added 2 to every dimension because you pad on the right and on the left, on the top and on the bottom. So you have to remember that, okay? All right. So like we can also look at this and we can say, okay, I guess, yeah. So this one does actually work. If we try doing doing exactly what we just did, we get 34 minus 4 divided by 5, which is 6, plus 1, which is 7, right? So let's actually do it. So we have our 4 by 4, and we have our 34 by 34. If we do it out with stride 5, we get that the output height is this, right? So this is our new formula, which is the input height plus 2 times padding. Very straightforward there, minus all this. So it's exactly the same except we introduce this new padding term, right? So if we do it out, we see that we get like 30 divided by 5 plus 1. So we actually end up getting 7, which is fine. So what we're going to do when we're doing our convolutions is we're going to decide what amount of padding we need and what amount of, or what strides work. So we'll decide both of those things independently, and both of those things end up being hyperparameters for our model, which if we were to tune all of them would end up being very difficult for us. If you remember, us doing just like adding a single parameter into our hyperparameter tuning ended up making it take a ton longer. So we need to, figure this out in some other way other than just trying them all out. And in general, we can just sort of play around with them and make them work. We don't need to be as precise with this, or in general, people don't. If you come up with a good way to find the stride and padding that you need that work best, that would be really interesting. But in general, there's no method that I know of. All right. So what about color? So we're talking about Safar. We're talking about Safar 10, which is 32 by 32 color images. And we haven't talked about color at all. So we have our 32 by 32 input that we've been working with. But in reality, like with our 4x4 convolution, but in reality, we actually have 3 channels to our input, right? We have red, green, and blue. So what we end up seeing is that if we want to apply a convolution, onto our input where it has 3 channels, we're going to need that our convolution also has 3 channels. So every one of these 4x4, or this 4x4 convolution will have 3 different channels. It will convolve over all 3 of those channels. So when we get our output, right, we get our 29 by 29. This is with stride 1, like we talked about earlier. Would anyone like to guess how many channels our output has?
Three.
Who said 3? Well, who
Yeah,
said?
it's 3.
It is 1. So it's not 3. It's not 3 at all. It's 1. So what's actually happening is we have 1 filter, and at every point where we're doing this, we are adding up the multiples of all of them across all dimensions. So we did our multiplication and addition like on our 1 dimension before, and now we're just doing it on 3 dimensions. So these values are actually just going to be higher. They're just going to be larger. I mean, if it's between 0 and 1, it won't be, but we're just adding up more per filter. So these values are adding up more. Okay, but it is still 1 channel. So that's the way that this works. Okay. Now let's talk about it a little bit more. All right. So let's take away that little convolution, right? We'll let it fade away. And let's try adding multiple filters. So far we've only used 1 filter this entire time. We've been just using 1 filter and laying it over. But what if we had a lot of filters? So in general, this is actually a pretty normal way to draw a bunch of convolutions. So you could count them if you want. I'm going to say that there's 10. There's not, but I'll say that there's 10. And what we see is that this actually will take in 3 channels, but will have 10 filters. So each of the filters will have 3 channels, but there will be 10 of them. So what we end up seeing is that we get our output of the same size, but anyone want to guess how many channels this one has?
10.
Yeah. There's 10. So there are 10 channels in our output now. So not only now do we have to keep track of our stride and our padding and our dimensions, we now also have to keep track of our channels, which is an extra dimension, really. Like it is with the input, is a 32 by 32 by 3. And so with this, we have a 29 by 29 by 10. Or in fact, it's more common and a better etiquette to say 10 by 29 by 29. So if you write it down anywhere, put the channels first and then the dimensions. All right? Cool. So let's talk about this now. I guess I forgot to put animations on here, but you get the gist. Let's talk about multiple convolutional layers with multiple filters, all right? So say we take our input into our first layer of convolutions. So we have 3 input channels and 10 output channels. So every convolutional layer will have input channels and output channels. Even our example earlier has an output channel. Its output channel just happens to be 1, all right? So when we're defining our convolutions in practice, we're going to have to keep track of that, and we will have to say what our input and what our output channels are. So if we have 10 output channels from here, then we know the next layer, which only has 5 filters, will have 10 input channels and 5 output channels. So each of these filters right here will have 10 dimensions. They'll have 10 different channels in each of these, but there will only be 5 of them in total. Okay? So we'll continually do this. We go from 3 to 10 to 5 to 11, right? That's the progression that we're doing in this example. So we see at the output of this entire thing, we would actually end up with an 11 by whatever shape, all right? And in each of these, it is totally possible that it is also reducing the width and the height. So we could end up with totally different dimensions than we started with. So we have to keep track of them layer by layer. All right? Okay. So I just want you to look back at this again with the new insight that you've seen and see that each of these little blobs right here, each of these little pictures actually represent a single filter. So we can actually look at this and we know that we have 3 channels on our input and we have, 30 different filters here, which means that our first convolutional layer will have input channels 3, output channels 30, right? And we can keep doing this. And in fact, you can see here, too, that the size of each of them is actually the same. So they've picked their stride and their kernel size and their padding such that the images will stay the same size, or each of the filters will stay the same size as they go. And we will have a whole bunch of them. All right? So it's interesting. Or actually, kind of disregard that, actually. I made a mistake. Because these are the kernel sizes. So the kernel sizes are actually different, too. So I messed that up. Anyway, so you can see how the progression looks in terms of visualizing the filters. Right? All right, cool. Now I'm going to do the batch normalization slides again because I think that that's probably something that didn't entirely land on everyone in terms of its importance. But I'm sure, hopefully you guys can fill in some gaps for me as we go. All right. So we initialize our weights. Let's arbitrarily choose that we're going to initialize our weights from 0 to 1 as a normal distribution, a Gaussian distribution. If anyone doesn't know what that is, that's a bell curve. Very easy. With mean 0 and standard deviation 1. All right. So our things will be in general, will be between -1 and 1. Okay. So when we do our first matrix multiplication here, but by our weight matrix, which is initialized this way, we'll see that we'll roughly get a bell curve. Right? We can, if our data is very nice, we might get a rough bell curve here. But let's imagine that we do more layers of matrix multiplication with weights that are initialized similarly. All right? So let's do another one. What do we expect to see happen to our distribution?
It will narrow down.
It will narrow down, exactly. So because this is in general between 0 and 1, we'll see that numbers multiplied by a number between 0 and 1, or -1 and 1, will become smaller. So we actually see that it will reduce in standard deviation, and we'll get an even sharper bell curve. And then as we do multiple layers of this, you see that it gets sharper and sharper until eventually it essentially disappears. All right? This doesn't immediately feel like a problem. I mean, we can always at the end still read, if we're getting score values, we can still read them. We still have one that's higher than other ones. It doesn't seem like from a feed forward perspective, this isn't the end of the world. It's not great, but it's not the end of the world. We start getting a problem though when we want to actually optimize our network, okay? So when we're doing this, what happens to the gradient as we reduce the standard deviation of our distribution? Just someone.
Vanishes.
It vanishes, yeah. So this is the vanishing gradient. That's the term for it. So this approaches 0 as we do multiple layers, and that means that the partial derivative of this weight matrix approaches 0 as well. Because if we do our partial derivative through this, we multiply by this value, right? And we end up with a near 0 gradient, which means that we're not learning at all. All right. So the idea that we have is batch normalization. Of course, I'm sure people remember at least the gist of it, but we have to talk first about batching. And hopefully now, understanding channels, it has a slightly more impactful meaning to you. All right. So we're gonna do some batching. All right. So we take our image, we have 28 by 28 image, but we take 10 of them at the same time, and we get our new dimensions, which are 10 by 28 by 28. So those are our new dimensions. Okay. So we feed the whole batch in and we update based on the entire batch. So we are finding our gradient of this entire batch of data. It does require a little bit of different coding to actually take the gradient over these dimensions instead. But in general, we are just creating bigger weight matrices. We're initializing bigger weight matrices when we do this. All right, that's the gist of it, is that we're just doing that. All right. So normalization. Normalization is very straightforward. All it is subtracting the mean from your data and then dividing by the standard deviation. This gives you mean 0 and standard deviation 1. Simple enough. That's just the average, and the standard deviation is this equation, which, if you don't know it, is just this equation. It is the second moment of your data. You can just sort of take my word for it. I'm sure all of you know roughly what a standard deviation is. All right, cool. So if we're doing this, right, when we actually implement batch normalization, what we're going to do is we're going to do, as you might expect, subtracting the mean and subtracting the standard deviation over our batch. So it's not going to be over the image, it's going to be over the batch, right? And we're going to get our new x value, our mean-centered and standard deviation 1 batch. What we're going to do then is we're going to do something that seems very counterintuitive at first, which is multiply it by some other new parameter that we're introducing and add another new parameter to it. So what is hypothetically possible is that we could have this value, so these values will be learned as we update our network. It's possible that this value will exactly match our standard deviation over the batch, and that this value will exactly match our mean, and what this is doing then is exactly undoing the operation that we did before. So it seems counterintuitive to have these, but in reality, it allows us to modify how we're doing our normalization, and that is important. So we're essentially changing what these are. So this would be like this divided by gamma, and this would be plus beta. So we're doing some different stuff to it. And this is how we implement it. All right, and this is a computational graph. Hope you all remember computational graph. You can see immediately that it is maybe a little bit complex to implement. You probably are thinking these are all like easy partial derivatives. Fine. I can tell you from experience that it's hard to do. You have to do it piece by piece. But this gives you an idea of what doing something as simple as normalizing your data can look like in terms of actually implementing your gradient descent. It becomes difficult. You can't just throw in random stuff, and then you can't just modify your data however you want unless you're willing to put in the work to find the gradient of that. And if the gradient is hard to find and you have to do it a lot of times, you are killing your runtime. You're killing your training time. You can't do that. So keep that in mind. All right, that's the batch normalization review. Now we'll continue. All right. Oh, man. I've got an animation there. Whatever. So let's look at a particular example, okay? So this is an actual image from the Safar 10 dataset. It's a little frog. Say hi to the frog, everyone.
Hi, frog.
Thank you. Thank you, Eddie.
Hello, frog.
So the frog is a 32 by 32 by 3. So it's 3 by 32 by 32, which means it has 3 channels, right? It's RGB, obviously. What we're going to do, though, is add a batch to it. So we're going to take some batch size, right? Let's say, I think I chose 10, right? So we're going to have a batch of images of frogs, or images from the dataset, and the dimensions end up being 10 by 3 by 32 by 32. And this is the standard ordering of the dimensions of these objects, so keep that in mind. We're going to have the batch size, the channel size, and then the width and height, okay? So what happens then if we put this image, a batched image of like color, through a layer of convolution, okay? So let's say that this has 3 input channels and 6 output channels. There's 6 filters, each that take in 3 different channels, okay? Let's say our stride is 5, 5, so that is 5 in both directions. Our kernel size is 5 by 5, so each of these are 5 by 5. Our padding is 4 by 4. What is the output of the convolution? What is the output size? Ignore this, pretend you don't see it, and try to calculate it on your own. All right? Like I'll give you 30 seconds. You're probably less motivated to figure it out now that you already know the answer. I'm gonna someone say the answer when they get it on their own. If you give an incorrect answer, I'll respect you a little bit more. Do actually try to go through the process, by the way. you're going to have to do this. Even with PyTorch, even with all these lovely things, you're still going to have to calculate this at some point. You have to do this every time you're implementing convolutional layers. You need to be able to figure out what these are. You aren't going to need to know the batch so much because your PyTorch can handle that. Your data loader can do that for you. But you do need to keep track of like what the output size will actually look like. All right?
Maybe it's a kind of stupid questions, but how do you know like the output channels? Is that one given?
So it's given. So it is the number of filters in your convolutional layer. So we have 6 filters here. You can count them. There's actually 7, but we'll say there's 6. It is defined when we're doing this in PyTorch, and when it's not in PyTorch, it's something we're going to have to implement. But essentially, it's just another dimension that we're putting onto it. So in general, these convolutions will be of dimensions output channel by input channel by kernel size. So that will be like their dimensions. You don't need to know that so much unless you're going to implement them yourselves, but it is good to know. All right. So
okay, I see.
Yeah. So we do in fact get the shape 10, 6, 8, 8. 8 and 8 you can probably figure out on your own. The output channel is directly taken from this. So the ordering is going to be still batch, channel, width, height, like we have always been doing. So the batch will stay the same size the entire way through until the very end. All right. So we don't actually change our batch size in any of our layers. So keep that in mind. We don't want our convolutions to change the batch size, then we're throwing all sorts of things away. Okay, cool. All right, it's time for a Kahoot. It's Kahoot time. It's Kahoot time. I need to go back. All right. So I'm gonna give you the pin. You go to kahoot.it. Okay, you got it. All right. It's loading the game pin for right now. All right. Let's turn it down a little bit. All right, are you ready? Who's ready? All right, cool. So that's the pin. I hope you can all see it. This one's going to be a little bit shorter because there's less things to test you on, but I'm going to try to make sure that you all know how to do this sort of stuff. All right. Is that everyone? I think so. I'm going to give you like 10 more seconds to join. All right. All right, cool. Let's do this. How many parameters can be adjusted in a batch normalization layer? That was the correct answer. We can only update our beta and gamma values. Everything else is not parameters. Cool. All right. Nice. Looks like Decade is taking it so far. All right. Next one. Imagine we have a network of this structure. What is the size of the output? So 3 by 32 by 32 with 3 input channels to 20 output channels with stride 1, kernel 3 by 3, and padding 1. That's pretty dramatic. Ooh. So a lot of people put the batch. If we look at the image, there is no batch dimension. It's a throws you off.
We've been tricked.
You have been tricked, and you fell for it.
No, I didn't. That's a lot.
So yeah, in fact, it is 20 by 32 by 32. All right. Well, now all of you who just got tricked. Let's see. Ooh, nice, nice. Now we're gonna do it again, except with batching and a harder problem. Ooh, yeah. So this was in fact one of the trick answers. So if we look at it again, after we implement the padding, right, we will get a 10 by 10, right? And we see that if we try to do like 10 minus the kernel size is 7 divided by 3 is not a whole number. So we actually cannot do this with the given things. The trick was that it is in fact adding 2 to the dimensions, not just 1. Yeah. So gotcha. And in fact, actually, if it was doing that, then it would actually be this one, just so you know. All right. Or I think actually, wait, was it? No. No, it was this one. Sorry. Okay, cool. Looks like Adam is rearing ahead. Let's get more drama in here. I could kick Adam. Can I do that? Oh my god. All right.
Yeah, you can.
No, don't
you have
do
all
that.
the power.
Yes,
Alright.
yes.
All right. If someone dethrones Adam, I want to give him a prize. I think they'll get to rename Juan
Who
again.
can share the prize with me? Who will
No
share
one.
the
If you
prize
share the
with me?
prize with
Let's go
Adam, then
ahead.
you're out of the club. All right, cool.
Oh.
All right. So I'll let whoever wins can rename someone. I don't know why that's my go-to prize, but it's easy and it's pretty dumb. All right. Let's go. Next question. If we attach a fully connected layer, that's just a weight matrix multiplication, layer to the output of this network to classify, what would the dimensions of the fully connected layer be? So we're trying to classify 10 different classes, and we're taking the output from here. This one's a bit harder. Five seconds, so click something. All right, so in fact, it is this. I would give partial credit if Kahoot allowed me to for this question, for this answer too. This is a good point to point out that the standard form of showing the dimensions of one of these affine layers, they're called affine layers, one of these fully connected layers, is input into it to output. That's the size of it in general. So that's the standard. So get used to that, I guess. I don't know. All right, next question. Oh, Adam stayed in the lead. Oh my god. Chabe is getting close, but not quite. All right, let's take a look.
I forgot to answer the first question.
Sure thing, Nick. Sure thing. All right, 2 more to go. Let's see if anyone can steal it. All right. If all of our weights are initialized to normal between 0 and, or mean 0, standard deviation 1, what would this converge to after we added multiple layers? Or as we add more layers, what does it converge to? Okay, cool. All right, yeah. So it does in fact converge to 0. I'm sure everyone can know why. Besides one, I'm sorry. But yeah, it does get closer and closer and closer to 0, which means that it does in fact converge. Yeah. All right, cool. Let's see. Adam's staying up there. Not Ryan is down there. Not me is down there. Brun Chabe. All right. Let's take a look. Last question. Is it a hard one? I don't remember. Which of these nonlinearities might cause multiple layers to converge to 0? So if we put multiple layers and nonlinearities in between them, which of these might cause it to converge to 0? Faster, I guess.
I am getting dethroned.
I have no idea.
No, it's a harder one, I think. It's a more theoretical one. All right, very random distribution here. I would most second answer. I really genuinely want to give partial credit. This was all of them. It's more correct though to say sigmoid and tan H. So if you think about it, tan H and sigmoid both cause your distribution to become closer to 0 and 1, in that range. Or I guess sigmoid or tan H goes to -1 to 1, but both of them squeeze your outputs closer to 0. ReLU does for negative values, but not for positive values. And in fact, a big reason that ReLU is used more than these other two is the fact that it doesn't do that. It has two big properties. One, that its derivative isn't 0 anywhere where it's positive. It doesn't matter if it gets huge, it will still have a big derivative. And two, it doesn't cause your values to get closer to 0. Those are the two things that are helpful about ReLU. And sigmoid and tan H don't do that. So cool. Let's see how it turns out. I feel like we're gonna have a mix-up now. Third place, Bruh.
Bruh.
Second place, Chabe. And I expect first place.
Yeah.
To not be Adam? Oh, it's Adam. Shit.
How did I win?
Nice. I think you won because they were hard questions, and I think just if you had wrong intuition about it. All right, cool. Well played. Well played. All right, cool. Let's get back to it. All right. That's Kahoot. That's Kahoot. That's the ball game. I guess I'll let Adam rename someone, even though I said that it would only be someone who dethroned him, but fine. All right. Let's go. So, that's Kahoot. Do you want to rename someone now? If you have something in mind, you can go for it.
No, I don't have something in mind, but I will use your trick.
All right.
Everyone shout out. Whose name do you want to change? Adam.
Adam.
Yeah, go ahead. Change my name. That's all right. What do you want to
change it too, yeah.
It would be.
So I'm not choosing it. You're choosing what it is, or I think we should crowdsource this actually.
I'm asking the people.
Adam with more A's.
Okay, go ahead.
I like that. All right. There you go. There we go. Okay. We're done with Kahoot. Adam won. You can tell because his name's all fucked up. All right, let's move on. GANs, that thing that I promised you at the way beginning. All right, let's actually talk about them. So what is a GAN? Does anyone who's heard of GANs before want to tell me? Someone said they've heard of them before. You better know what it stands for if you've heard of them before. I'm looking at you, Ryan.
Generative adversarial network.
It is, in fact, a generative adversarial network, GAN. All right, so how do they work? What do they do? So let's take some data. Say we have some data. I think one of the easiest examples is think that these are faces, right? That puts an image in your face. So this is a data set of faces of some size, of some standard size. What we're going to do is we're going to define a network called the discriminator. The discriminator will have an input of the size of our data, right? And it will take in the data and will output real. So it has a binary output, real or fake, and when it gets the data, we want it to say real, okay? Now we're going to do something kind of weird and make a second network, one that we call a generator. So the generator will take as an input some size of random noise. This is another weird thing for us to decide to do, but we're feeding in random noise into our generator. And from our generator, we are producing output of the same size as our data. And now we're going to feed those generated images into our discriminator, and the discriminator should output fake. So it will distinguish between fake and real data. Now, the trick here is that the discriminator might not. If it were to say real, then what we know now, or the way that this system works, is that if the generator outputs an image that goes into the discriminator and the discriminator mislabels it, then the generator is reinforced. If it outputs fake, then it is negatively reinforced, or it is changed a lot, or instead of improving itself, it is changing itself. The discriminator has the exact inverse of training. So if it's fed a generator image and it outputs fake, it is positively reinforced. If it outputs real, it's negatively reinforced. And we can, in fact, still now alternatively use the data. So we use the data in one step, then we use the generator, then the data, then the generator. And when we do that, we'll see that when we input the data, the discriminator will be trained to output real. And we put in the generator, it'll be trained to output fake. And then the generator will be trained to fool the discriminator, all right? So the real thing that comes out of doing this, we could train this for a huge amount of time, and then if we were to input random noise into the generator, it will output images of faces, and good ones. So this sort of all these fake faces, if you've ever seen something that says this face was generated by a computer or by AI or something like that, this is almost definitely what they were using. So it is a pretty simple conceptually. I mean, it's very interesting. It's a clever idea, but it's pretty simple conceptually. But it has very good outcomes. So we see a lot of good stuff from this. Let's talk though. Okay, I was going to show you. Which one of these two faces do you think is fake? So one of these faces was in fact created by a GAN. The other one is a picture of a real person. Which one is which? We'll have a vote. We'll have a vote. I'll give you a second to look at them. All right. Check them out. Maybe there's some pixels that are wrong. Okay. Okay. All right. First, so pick yours in your mind. All right. Who thinks that the woman is fake?
Me.
All right. About half. Okay. Cool. And who thinks that the guy is fake?
Me.
Yeah.
I'm not going to tell you. So, I feel like I actually genuinely shouldn't tell you. It's a lesson. It's a lesson in this is in GANs are good. It's the woman, by the way. The woman's fake.
You just told us you wouldn't tell us.
Or I'm lying. You don't know. You'll never figure out. All right.
Would you ever lie to us though?
This entire thing is actually, none of this is actually real. I'm just lying to you constantly. All right, yeah.
Oh,
All
I
right.
see.
So here's a visualization of essentially what's happening. we have some data, right? We have the generator outputting some stuff. We have the images, or we have so we have in our space of possible images, right? Of possible data of a certain size, right? I'm projecting it down to 2 dimensions. You're just going to have to believe that I can do that. But we say that, like, this is it, right? So all of these red dots are faces, right? And all of these green dots are things of the same size that aren't faces, okay? What we're doing when we're training our discriminator is we're learning how to distinguish between these two, because initially it's just data points, and we're learning where the boundary is between them, like where the boundary is where once we cross that threshold, it becomes face images, okay? So we create that boundary by training our discriminator, and then what our generator learns to do is to sort of emulate this boundary and then learn how to sample from inside of it. So what we're doing is, like, it's a little bit more complicated than this, because we're essentially, in the generator, we're converting a Gaussian distribution into our data distribution, which is, like, it maybe is a little bit conceptually hard to understand why, like, that makes sense. And then we are, like, sampling from that distribution, and with the discriminator, we're doing something kind of similar, but not actually. So there are a lot of parallels between them, but you have to understand that I'm really just waving my hands at this right now, okay? So again, we learn how to, like, find these boundaries and then sample from inside of it. And this right here would be an example of a fake face that we generated. I'll put a link somewhere to the actual GAN paper so that people can read it. It's a bit more complex than this. I'll get into a little bit more of the complexity right now, but it is more complex than I am going to get into. All right, so let's talk about this. What's the loss, okay? So we have a binary, we have binary options, right? We have a 1 or 0, right? And I'm sort of waving my hands at saying that we're reinforcing the network, right? We're reinforcing the generator. We're not doing reinforcement learning. We're doing back propagation. So how do we actually define our loss so that this makes sense? I'll let someone give a guess if they want to. You're probably going to be wrong, but you also might be right. You might be really close at least. I'll make it less scary. You'll definitely be right. All right. Someone guess.
But we already know that you lied to us, so.
That's true. I was lying the first time. There you go.
What was the question, Cooper?
So I said with the GANs, right? If we go back here, I said with the GANs that we are distinguishing here, and then I said, like, we're going to reinforce the generator when it tricks the discriminator, and we're going to like reinforce the discriminator when it distinguishes between them. But what does that actually mean in terms of actual, like, loss function? Because, like, we can do reinforcement learning where we take, like, reinforcement signals and propagate them and all that stuff, but we're not doing that. We are doing back propagation. So how do we do that? I think I'll stop asking you because it is a probably too hard of a question. And the answer is kind of clever. So I don't think anyone will have any guesses. Does anyone have any guesses? All right, that's fine. That's fine. So our answer, and I will probably not explain this out fully because it might take a little while, and I don't know if I'm 100% qualified to talk about it, but here is the loss function, okay? So there's a lot of statistics going on here, and there's a lot of interesting things about this loss function. We'll break it down, though, okay? Don't just, like, think that this is the whole explanation and we're moving on. So let's break down each of the terms. So E of x is the expected value over real inputs. So this term right here in our loss, first off, is only when it's real inputs. That's the first thing to acknowledge, is that this is an average over just the real inputs, give us log of d of x, okay? So you can think about what happens when d of x is the output of the discriminator when it's 0 and when it's 1. You can think about that and how this changes, okay? E of z is the expected value over the noise, which is the input into the generator. So that's the actual input, so we have to go all the way back to there. But essentially, when there's a fake image, when the generator is used, this is the average over those cases. All right? And then we have d of x is the output of the discriminator. So this is the output of the discriminator when given an image. And G of Z is the output of the generator given its distribution, all right? And then log is log. So hopefully that that's okay with all of you. All right. So let's look at what this is doing. I will not go into it fully because there is a little bit of statistics that make this work, but we can just sort of get an understanding of it. Okay. So we have our log of d of x. When d of x is 0, what does this become? What is log of 0?
Negative infinity.
I think so. I actually don't know, but I think so. So negative infinity, so it becomes very negative, right? And then we have, I think, so this is the part where taking the expected value over them is important because we aren't ever actually going to have 0. We're just going to have like low numbers. So we're taking the expected value over a bunch of possibilities. Hey. Okay. And what is it when it's 1?
1.
It's 0.
0.
0.
Zero.
Sorry, 0, 0.
Yeah.
Right.
So we're gonna, like, I guess you just sort of have to believe me that when d of x is nice, when d of x is correct, so when it says that x is real, which is d of x is 1, then this becomes 0, and the term for loss of this becomes 0. Then we have looking at the cases of EZ, and essentially what we're doing is the output of the discriminator, right? And the output of the generator, and then we put it through the discriminator, and then we have the exact opposite here, right? Where it's essentially the inverse of this, where when it's, so instead of like this normally, it's essentially when this is 1, this becomes 0, and when this is 0, this becomes 1. You know what I mean? So this is the inverse of this, and it has the same sort of properties as this. So it's just a little clever symmetry between them, and it gives us a binary classification. And this is, in fact, the same as binary classification error. So if you look up BCE loss, you'll see that this is not exactly the same, but is comparable to it. All right. So that's good. That's good. I hope that makes sense. Does anyone have any questions about that one? The tricky thing here is us using the expected values. Everything else is, I think, fairly straightforward. All right, cool. So now we're going to do GitHub. So who has used GitHub before?
Me.
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 GitHub.
Me. I
Okay.
used it.
All right. If you have not used GitHub before, now's a pretty good time to do it. I mean, you should really use GitHub. You can make an account and download it here. I will share the slides real quick. Boom. All right. And now, all right, ready? Boom. So I'm going to just assume that everyone has it installed unless someone stops me. We can vamp if someone needs time to install it and all that. No one's stopping me. I'm going for it. All right. So I want you all to clone this repo. So go do that. If you can also like look it up. It's pretty easy. All right. Just clone it somewhere. It doesn't really matter. This repo was in fact not made by me, by the way. I just want to point out. So I forked it so that you guys can mess around on it. But this is the PyTorch GAN library that someone made. It's very nice. All right. So I'm going to give it like 2 minutes for you all to clone it and get it ready. All right, all right. Someone just be the spokesperson and tell me when they have it cloned, and I'll assume that it'll be a little bit after they get it done. People have it done. Well, did you not all just have your terminals open, ready to clone a new repo?
That's my
I
bad.
have repo.
I got it.
All right, cool. I'll give it like another 30 seconds then.
I got it too.